In the last video, we talked about what a ring buffer is conceptually. It's kind of like a merry-go-round with no clear beginning or end. That's why we call them ring buffers or circular buffers. But in practice, a ring buffer, like most other data structures, is just an array with some special rules. We control how this array can be accessed and modified by defining special functions for reading from and writing to it. Any programmers using our ring buffer cannot just access and modify the array using a regular index lookup. In this video, I'll be showing how a ring buffer can be implemented using good old-fashioned C. First, we'll create a C structure to represent our ring buffer. A C structure is just a collection of several variables, and if we add the type_def keyword in front of it, later on we can declare variables to use our ring buffer structure as their type. We're going to need three variables in our ring buffer: the read and write pointers we use to access the array, and the array itself. And this being C, we need to define what type of data they contain. The array is easy, since it just depends on what kind of application our ring buffer is used for. Let's say our ring buffer is used to process keyboard input, like we mentioned in the last video, so our array contains characters. The data type for the read-write pointers is a bit trickier. We have two options. As you may know, each block of data in an array can be referenced in two ways, either by its index, which is its position in the array, and its memory address, which is its position in the entire memory of the computer. So option 1 is to set the read and write pointers to represent a data block in the array by its index number. So for example, if the read pointer is pointing to the first element of the array, then its value should be 0. In this case, I'd set the type of both read-write pointers to be an unsigned integer, or size t, which is a special data type in C that is specially formatted for representing the size of data. Option 2 is to set the read-write pointers to represent a data block in the array by its memory address. So if, for example, I want to record that the write pointer is pointing to the fourth element of the array, then I'll set the value of the write pointer to be its memory address. In C, if a variable contains a memory address, its data type is called a pointer. But in addition to being a pointer, we need to also define what type of data it points to. Since our ring buffer contains characters, we define our read-write pointers to be character pointers. So how to choose? Well, for now, let's just use the memory address implementation and then compare the two later. Since we're not going to allow those pesky programmers from freely accessing and modifying the array however they please, we need to define a read function for getting data off of the ring buffer and a write function for putting data onto the buffer. Let's start with the write function. We start with an empty ring buffer. We have an empty array with both the read and write pointers pointing to the same data block containing its memory address. They could be pointing to any of the blocks in the array, but let's just say they're pointing to the first block for simplicity's sake. Writing a new piece of data is simple. Remember, we write new data to whatever data block the write pointer is pointing to, then advance the write pointer by 1. So let's write the new data to the first element. Since the write pointer is a character pointer, assigning the new data directly to the write pointer is wrong, since the write pointer is only meant to store the address of a character and not the character itself. It'd be like accidentally changing your address when all you wanted to do was have something sent to your address. We need to dereference the write pointer with a star symbol first, before we can assign the new value. Now that the new data has been put into its place, we can move the write pointer forward. Now we want to change the address contained in write pointer, so we'll operate directly on the write pointer by adding 1 to it, this time leaving out the star symbol. Now simply adding 1 to the write pointer is okay up to a certain point, until the write pointer is about to go out of the bounds of our array. When this happens, here's what we do. We move the write pointer back to the beginning of the array. Simple. We can check if it's about to go out of bounds by comparing the address stored in write pointer with the address of the last element of the array. In C, we can get the address of any variable by using the ampersand prefix. So the address of the last element of the array would be ampersand array index 7. So after increasing the right pointer by 1, we check if it is larger than the address of the last element in the array. If so, we set right pointer to store the address of the first element in the array, ampersand array index 0, effectively moving it back to the start. Great, but now there's a problem. Our ring buffer is full, and our read-write pointers are both pointing to the same data block. Look familiar? It's the same situation as when the ring buffer is empty, but a write operation on an empty buffer and a full buffer are very different. We need a way to differentiate between a full buffer and an empty one. Once again, there are multiple ways we can go about doing this, but for simplicity's sake, we'll just use a Boolean variable, something that contains either true or false to track whether the buffer is full. It's false by default, but if the write pointer is equal to the read pointer after it's been incremented by 1 in a write operation, then we set it to true. Every time a read operation occurs, we set it to false. Now that we've established how we're going to differentiate between a full and an empty buffer, let's get back to our write function. So what happens when we write to a full buffer? We have to move the read pointer forward by 1, because we're going to overwrite the oldest piece of data in the array, meaning that now the oldest piece of data will be the next element. Once we've moved the read pointer forward, it's the same as usual. Write the new value to the data block pointed to by the write pointer, move write pointer forward by 1. So really, we just need to add an additional block of code at the start. But we're still missing one thing. We need to check whether the buffer is full after we've advanced the write pointer. If it is, then we set the Boolean variable full to true. And that's our write function. I simplified the code during the explanation, so here's the full code. Mainly, I left out the ring buffer C structure when accessing its variables. Now we can implement our read function. Now, whereas the write function had to account for writing to a full buffer, the read function needs to account for writing to an empty buffer, because obviously you can't read anything if the buffer is empty. So how do we detect that? Well, it's quite simple. We know that an empty buffer will have the read and write pointers pointing to the same element in the array, and we already created the full variable to differentiate between an empty and full buffer. So to determine that the buffer is not empty, all we have to do is check for two cases. Either the read pointer and write pointer are not equal, or if they are equal, then the Boolean variable full is true. Once we've determined that there is something to read in the buffer, we can start the read operation, which is more or less the same as our write function. First, we take the value pointed to by read pointer and store it in a variable. Remember, read pointer is just a pointer, so we have to dereference it to get the value it points to. We then move the read pointer forward by 1. Then we set the full Boolean variable to false, since we've just taken an element out of the ring buffer. Finally, we check if read pointer has gone out of bounds, and if so, we move it back to the first element. And at the very end, the function returns the character that was pointed to by read pointer. Now you might be wondering, once we've read a value, why don't we erase it from the array? Well, it's not necessary, because when the write pointer inevitably gets here, we'll just overwrite the value, so it doesn't make a difference. And there's no chance we'll read the value by mistake, because the read pointer can never overtake the write pointer. Because once the read pointer catches up to the write pointer, it means the ring buffer is empty and there's nothing to be read. And that's our read function. So far we have our ring buff C structure, a function for writing to the ring buffer, and a function for reading from the ring buffer. Now there are still more functions we have to add to our little ring buffer library, like initializing the ring buffer, or destroying it once we're done with it, or calculating the remaining space, and so on. But I'll leave that to another video. To conclude, let's go back to the start where we were considering our ring buffer C structure. For the implementation, I stored the memory address of the array element in the read and write pointers, but the other option was to store the array index instead. Let's see how that would change our read and write functions. What you'll notice is that the code is a lot more readable. It's a lot easier to understand where the read-write pointers are if we record the index number of the element they're pointing to. There are some cases when using pointers provides a performance benefit, but it really depends. For this example, I just decided to use pointers and memory addresses because I wanted to practice. So that's the end of the video, and thanks for watching.